Welcome to Module 9, Debugging and Troubleshooting. In this module, we shift from writing code to fixing it. Every programmer writes bugs, so learning to find and fix them calmly is one of the most valuable skills you can build. Over 11 lessons and a final project, we'll learn to read the clues your code gives you and fix problems with confidence. Here's our roadmap. We start with what debugging really is, then work through Python's error types, tracebacks, and print debugging. From there, we tackle logic errors, test cases, the VS Code debugger, and the trickiest bugs in loops, lists, functions, and exceptions. We finish with habits for cleaner code and a hands-on final project. Let's define our terms. A bug is simply a problem in your program. It might stop the program, show an error, produce the wrong answer, or run forever. Debugging is the process of finding and fixing those bugs. The key mindset shift here. Debugging is not guessing, it's investigating. Think of yourself as a detective, following clues. There are three main types of bugs, and the first is a syntax error, where Python can't understand your code. But logic bugs are just as common. In this example, a discount is being added to the price instead of subtracted. The code runs fine, but the result is wrong. Once we change plus to minus, the calculation is correct. Sometimes the value looks right, but the data type is wrong. Here, input always returns text, so adding two numbers together joins them like strings. Wrapping each input in int converts them to numbers, and now the addition works as expected. Always check your data types when the math looks off. In Lesson 2, we reframe errors. A Python error happens when Python can't complete your program correctly. But an error isn't just a problem, it's a message. It tells you what went wrong, where it happened, and what type of problem Python found. Instead of thinking my code is broken, think Python is giving me a clue. Here are the common error types you'll meet. A name error means a variable doesn't exist, often from a typo. A type error means you mixed incompatible types. A value error means the type is right, but the value isn't valid. An index error means a list position doesn't exist, and a key error means a dictionary key is missing. Learn these to diagnose faster. Let's look at a type error. Python won't let you join text and a number directly, so building a message with concatenation often raises this error. The clean fix is an F string. By wrapping variables in curly braces inside an F string, Python handles the conversion for us, and the message prints correctly. Lesson 3 is all about tracebacks. A traceback is Python's way of showing exactly where an error happened. It gives you the file name, the line number, the code that caused the problem, and the error type. Think of it as a map, pointing straight to the bug. Read the bottom line first to see the error name. Let's practice reading one. Starting at the bottom, we see a name error. Looking up, the problem is on line 3, where we printed the wrong variable name. The variable was created with an underscore, but used without one. Python is case and spelling sensitive, so matching the name exactly fixes it. Tracebacks get longer when functions call other functions. Read this one from the bottom. A type error from trying to concatenate a string and an integer. The lines above trace the path, showing exactly where the data types collide. The fix is to multiply the numbers instead of adding mismatched types. Lesson 4 introduces print debugging, the simplest tool of all. It means adding print statements to inspect your program while it runs. Instead of guessing what your code is doing, you print useful information, like what value is stored or what data type you're dealing with. It needs no special tools, making it fast for beginners. The trick with print debugging is to add labels and check types. By printing the type of your data, you can quickly reveal if your inputs are strings instead of numbers. Once you convert them using float or int, the total calculates correctly. Labeling your prints helps you keep track of which value you are looking at. Here's a classic runtime bug, the infinite loop. This while loop keeps printing, because the count condition stays true forever. The fix is one line, incrementing the count inside the loop. Now the count climbs as expected, and the loop stops cleanly. Whenever a loop never ends, check that the variable it depends on is being updated. Lesson 5 covers logic errors, the sneakiest bugs of all. The code runs and Python doesn't crash, but the answer is simply wrong. Because there's no error message, you must debug by comparing expected output with actual output. Always ask, what did I expect to see, and what actually happened? Order of operations often trips up beginners. Without parentheses, Python divides only the final score by 3 before adding it to the others, leading to an incorrect result. Wrapping the 3 scores in parentheses forces addition first, then the division, resulting in the correct average. If your math seems off, check your parentheses. Order also matters in if-elif chains. Python stops at the first true condition it encounters. In this example, the check for 70 comes before the check for 80, so a score of 85 incorrectly gets assigned to C. Ordering your conditions from highest to lowest ensures every score is categorized correctly. Lesson 6 introduces test cases. A test case is a specific input used to verify that your program produces the expected result. A robust test case includes the input, the predicted output, the actual output, and whether the test passed. Testing is critical because a program might work fine for one input, but fail for another. We categorize test cases into 3 types: normal cases for standard values, edge cases for boundaries or limits, and invalid inputs for bad data. Edge cases are particularly important to test, as many software bugs hide right at the boundary of a condition. Let's examine a boundary error. The original code uses greater than 50, meaning an order of exactly $50 fails to trigger free shipping. Changing the operator to greater than or equal to includes that boundary value, and now the code behaves as expected. Always test your exact boundary conditions. Lesson 7 covers the VS Code Debugger, a massive upgrade from manual print statements. A debugger allows you to pause your program mid-execution, inspect variable values, and step through the logic one line at a time to observe exactly how your code processes data. Mastering the debugger relies on 4 actions. Breakpoints pause execution at a specific line. Step over runs a line and moves to the next. Step into enters a function for deeper inspection. Step out finishes the current function, and continue resumes execution until the next breakpoint. These controls help you navigate complex code. In this debugger example, our price calculation contains a logic error. Stepping through the code reveals that we are adding the discount instead of subtracting it. By watching the variable value change in the debugger, we quickly identify the bug, change the operator to minus, and correct the final output. Lesson 8 addresses common bugs in loops and lists. We often encounter infinite loops, off-by-one errors, range mistakes, or index errors when working with lists. A crucial tip for debugging loops is to inspect the variables during every iteration, rather than waiting for the loop to complete. Infinite loops occur when a loop condition never becomes false. In this broken example, the count variable is never updated, so the loop repeats indefinitely. By simply adding an increment statement, we ensure the loop finishes once the count reaches 5. Always verify that your loop counter is properly updated. Modifying a list while you are looping through it is a dangerous practice that often leads to errors. As you remove items, the list structure shifts, causing the loop to skip elements. The safer approach is to create a new list and append the desired values, keeping the original list intact. Lesson 9 focuses on debugging functions. Common issues include incorrect argument order, missing return statements, wrong variable usage inside the function, and calling functions before they are defined. To debug effectively, test your functions individually in isolation before integrating them into a larger program. A missing return statement is a very frequent function bug. If your function performs a calculation but doesn't return the result, the caller receives none. Ensure your functions explicitly return the value they compute, so the main program can successfully use that data. Returning too early is another common error. If you place a return statement inside a loop, the function will exit after the first iteration, ignoring the rest of your data. Always double-check your indentation, and ensure the return statement is positioned correctly, so that it only executes after the loop finishes. Lesson 10 tackles exceptions. An exception is a runtime error that crashes your program if left unhandled. By using try and except blocks, you can intercept these errors, providing friendly feedback to the user instead of a raw traceback. Always examine the traceback first to identify the specific error type to catch. In this video, we'll cover the try/except structure. The key rule is to put only the risky code inside the try block. In the broken version shown, we catch a type error, but converting bad text to an integer actually raises a value error, causing the program to crash. Matching the except block to the actual value error is the correct fix. Here is a trickier exception mismatch. This function catches value error, but dividing by 0 raises a zero division error, so the handler never runs and the program crashes. By changing the exception type to zero division error, we successfully handle the situation and return a clean error message. Always catch the specific exception that your traceback identifies. Lesson 11 is about prevention, writing code that is easier to debug in the first place. Use clear variable names, keep functions small, and separate input, logic, and output. Avoid duplicating code, validate input early, and use named constants instead of mysterious magic numbers. The cleaner your code is, the easier it will be to debug later. Look at these 2 versions. The messy one uses single letters and multiplies raw input strings, making it unclear and broken. The cleaner version uses descriptive names like price and quantity, performs proper conversions, and formats the output. Good names allow you to debug faster because you never have to guess what a value actually means. Refactoring improves code structure without changing its behavior. The before version uses cryptic letters and a magic tax value. The refactored version renames everything clearly: price, subtotal, tax, final total, and uses the correct tax rate. Each step is now clearly labeled, making future bugs far easier to spot. Now for our final project, a mini store checkout system that we will debug end to end. The program has been seeded with real bugs, a missing comma, a key error, a name error, logic errors, and an incorrect tax rate. Our motto for this project is simple: do not guess, investigate. In this broken code excerpt, there's a missing comma between products. The loop starts at index 1 and skips the first product, and it tries to access a title key that doesn't exist. The fix adds the comma, loops directly through the product list, and uses the correct name key. It is both cleaner and correct. Here are the calculation functions. In the broken version, the subtotal is calculated with addition instead of multiplication and isn't returned, and the tax rate is set incorrectly. The fixed version multiplies, returns the subtotal, and correctly subtracts the discount. With the right rate, the final calculation is now accurate. That's a wrap. Remember, errors are clues, not failures. Read tracebacks from the bottom up, print or pause to see real values, compare expected versus actual output, and change one thing at a time. Clean code prevents future bugs. Happy debugging, because every bug you fix makes you a stronger programmer.